Okay, we will continue our talk on this uncoupled pitch and heave motions. Let me look at this estimate for added moment of inertia in pitch and also the damping, that is basically del Iyy and b theta. Okay. See, just like heave, if I have this ship here and if I took a section and if I have my sectional added masses was Az2d was my sectional heave added mass, and of course, we can also have that similar damping. I can always call this remember in previous class we mentioned about strip theory, that the ship was made in a strips and you are oscillating. Now, here what happened, see heave and pitch are so correlated that if I were now oscillating this way, it basically means sections are oscillating this way. So, what happened, as far as pitch is concerned, this has a sectional added mass, and what is my pitch moment of inertia, that is delta Iyy. It simply becomes integration of x square Az2d into dx over the length. Of course, you have to take the x measure from the origin of the system Cg. So, you see this how easily it can be found out. I will show this picture in this form again here, because it is easier to see a two dimensional form. So, I have a section here, let us say this much is my added mass, body is rotating like that. So, what I am doing is that this of added mass square of that, integrating over it. So, you see what is happening is therefore that if I can estimate pitch moment of inertia also from sectional heave added mass and similarly the damping part. And if you recall, we talked yesterday about different means of estimating that. One of the simplest one was also, of course, that as I said that if I were to take this a sectional beam B, my Az2d, if nothing is available, I will simply take it to be mass of this semicircle. How much is this? Pi b square by 4 into half, and of course, I can integrate that. If I do over dx, I get a good estimate. That is a very rough estimate. In fact, theoretically this is known as high frequency limit, theoretically, which means this is strictly speaking valid in deep water, which happens to be at high frequency limit. Never mind that part, but it is a good estimate. It is this estimate that is used in Barrel's formula, as somebody was asking, one of the students was asking, in vibration, because vibration is a high frequency phenomena. And when you take a hull, you vibrate it, what is the period? 1 second or so. Is there any wave at 1 second? No, waves are mostly 6, 7, 10, etc. So, 1 second is really high frequency, so you could use that. So, here also we can make a very rough guess. If not, as I mentioned in yesterday's class from that Lewis form, there are graphs and charts where omega versus those sectional, like these values are given for different values of beta n and b n by t, etc., etc. Various graphs are given. The one that we have talked yesterday, there are charts available of this as a function of sectional coefficient beta n, then with coefficient b n by t, and of course omega e. We have talked about that. There are charts available. It is only a simple matter of going to the chart, picking up for relevant value of that, finding out this. So, in one shot you can actually get always added mass in heave and added moment of inertia. Very simple. You simply make a like typically hydrostatic type. I have got x here stations. I end up getting this Az 2Ds. Then I have so called, if I want to use Simpson's multiplier, then I get this one, this gives me by sigmaing I end up getting here Az 3d, and here I use x square into Az 2d. Again I use Simpson's multiplier, again I get that. This will give me. So essentially in one table I can get both of them. Very simple, like straightforward. So heave and pitch are really related to each other. You can get from one table in any assignment or any problem. But this, having said that, these are only approximate formulas. See, the subject of this dynamics, like in water wave resistance, evolved for last so many years. Today, of course, we have got much more sophisticated programs, 3-dimensional CFD kind of codes to find out the same thing. But I am talking of practical estimate when you go to shipyard, when you have to make a quick estimate, when you are doing a first design. You are not going to run probably a code, very expensive code. However, for offshore structure, running such codes have become important. It has become a routine industry affair, where you do run available codes to find out these things. Anyhow, so this is only an estimate I am focusing on, so that you get a rough idea. As I mentioned repeatedly, that rough guess, somebody came to your company, you are in a shipyard, and try to tell you, give me a guess of your guess of the natural period, etc. You can quickly use this added mass and moment of inertia part, this formula, that is the high frequency formula, just this mass. It's slightly better than using a ky equal to 1 or some factor, slightly more accurate. So you can always get to that, So these are all various levels of approximation that you should know it. Okay, so this is the same thing will apply to damping. Exactly, damping is also available in this way, like damping function of sectional coefficient, sectional width and frequency. Okay, see, there is another very crucial thing I want to tell now from physical point of view of the behavior. Remember, when this goes like that, this is my theta or motion or z and this is my omega. We said that this low frequency part, this is the low frequency part dominated by hydrostatic force. This is my high frequency part, this is the damping part. Let's look at the pitch, how it looks like in this case. See, low frequency wave is like that. What happens, if you look at that, you will find out that the pitch is exactly in phase with this. That means it is always aligning itself like that. The low frequency part, one can show it will be in phase with exciting moment. Exciting moment is actually with phase with the slope. That makes sense, because you see why, I don't have to go through the maths to tell you, we can always use our own kind of logic to find out. See, it is taking very small frequency, means long time. So I have enough time. So when suppose water wave, suppose the shape is there, water wave become like that. There enough time for the hydrostatic to balance itself and make it aligned too, because this aligned position, of course, is where my hydrostatic force exactly balances. Since the frequency is low, means period is high, I have enough time for the body to adjust itself to the local slope, because only in the local slope my dynamic force, remember, dynamic moment becomes 0. See, after all, for equilibrium, in hydrostatic equilibrium, what I need, total hydrostatic force must be 0, moment must be 0. In this case, that happens. So this is why it follows that. Typically, remember, this makes perfect sense. Remember here, heave. This is what I will talk now. What happened to heave? Heave is also following this. Remember, if you go up and down, it is exactly here. You stand here, you find same local draft or same freeboard, which means it is simply going up and down with the wave. But now I will tell that there is an interesting phase gap between the two motions, which I will come in a moment. But before that, let's talk about this side. What will happen? Just the opposite. You will end up getting the ship, you you try to see that it is slightly this way. Which is more dangerous? Obviously, here you find out there is a tendency, because there is a phase gap, for water to go on top of the deck and here bow to come out and slam. So, you see here, because here when the water slope is rising, my ship is going down, right. So, there is a kind of opposite phase. So, once again the same thing is proven, that situation where dynamics are important becomes physically more significant in a sense, because that is more dangerous. After all, you do not want water to come on your deck. In fact, you will find out many of the small bows, of course not only for pitch reason, the bow is very much like very much up. Of course, this is for the wave resistance wave, but also for pitch to some extent. So, this is another extreme of that. So, we must realize this part. Where inertia is dominating, typically my exciting moment and my response are out of phase typically, or with respect to wave slope, and as a result when water is rising, ship is trying to go down. In this case the bow is going to go down when this is going rising. Okay. So, here there is a phase gap there. Now, let us look at this the phase thing, which is more easily seen, the relative phase between heave and pitch. In this case, I want to show you that, you see, when maximum, let us take an example of lower frequency. What we want to I want to tell you is that the maximum heave and maximum pitch usually do not occur at the same time, and which is good for us, because if it did occur at the same time for a given motion, you would have got a very large motion. Now, how do I see that? See, let us take eta. So, a cos curve. So, eta equal to a cos, what is eta x, equal to d eta by dx, that gives you minus, right, minus ak. This is right, sin kx minus omega t. So, this will be minus k, sin means it will look like, let us look another pen, minus sign will look like this, right. This is right. So, this is my eta x, this of course is t, this is my eta. Okay, this is right, right. Now, you see what is happening. Motion in low frequency, I am having my heave given by this blue line in phase with the blue line, that is heave is like that. This is my heave. Okay. Where is my pitch? My pitch is so, you can see that there is a phase gap between heave and pitch. When my heave is maximum, my pitch is 0. When my heave is 0, my pitch is maximum. Okay. You see that phase gap between the two. This is important, because when I want to find out what has happened when you are standing at some point, phase is important. I cannot add all the maximums together. See, I am standing at this location. We will discuss this later on. Ship goes down, also ship comes down. Supposing at the same time the amount it went down maximum, it came down maximum, you would have been much lower, but that is not happening. Usually don't happen. Why? Because there is a phase gap. The concept of phase is therefore very, very, very important. If I was to write this as z equal to za cos omega t, this will become theta a cos omega t plus a phase. Remember what we have done, we are always measuring the phase with respect to the input wave signal in our usual study with respect to input wave signal. In fact, what we do is that you see that if I always say that if I have eta equal to a e power of minus I omega t, you know, let us say this at x equal to 0, then I am writing my z to be z a e of minus I omega t into e of minus I beta z. This is all of course real part. What is this? This is nothing but cos of, we can say omega t, actually here I wrote plus, or you can write plus also, say you can say this way, because it is beta z minus cos means both are this thing, and theta is going to be real part of theta a what I found now, relative gap between these two is beta z minus beta theta. This is my phase gap between z and theta, but normally what I am doing, I am always finding between these two, and you will find out in later solution I will tell that we actually will write this way. I will write this to be real part of z a bar e of minus omega t, when this is equal to z e of I beta z. This term is known as complex amplitude. It is a complex number, because you see if I were making this part and this part, combine it, and I call that z a bar, obviously that number is a complex number, z a bar. So this signal is a sinusoidal signal in time with this amplitude, but this is complex amplitude. So for manipulation purpose, you will find out later on excuse me, for solution purpose we actually determine complex amplitude, because complex amplitude tells me directly phase and absolute value. So concept of complex amplitude is also important, we will see that eventually in when we actually do the calculation. Complex amplitude tells me that not only this value, also this gap, that is where it happens, the phase gap. Anyhow, my point of course is not so much to go into complex amplitude right now, but to tell you that there is a phase gap. Phase is extremely important. Just by telling me that I have this heave on so and so, pitch so and so, the story is not complete. You must also say when does it occur. That is important. As we have seen in this case, yes, pitch is so and so. Let us say here the ship is pitching by 3 degree, but when does 3 degree occur? Well, let us say it is heaving by 4 meter maximum. Is it pitching 3 degree when it is going 4 meter down, or no? This is what I need to also know, because without knowing that I cannot really find out the actual history of the ship motion. So phase is an extremely important concept in any motion that you have to understand. Without phase it is not complete at all. Okay. All right. Now I would like to get back to some means of determining added mass. Once again I go back to added mass because it is very important. Can anybody give me a guess about how I can experimentally determine added mass? Or why I am asking, I will tell you. How do I do that? You see, people will say that many people do not agree, all theories, they want an experimental verification, experimental measurements. Now resistance test, very simple. You have towed a model, just figure out how much is drag. As far as measurement is concerned, you have measured it, right? You just towed the model, find out the drag. What we debated is not how to measure it, how to extrapolate it. That was our main debate, scaling and all that. Similarly, for if I want a ship motion, maybe I will send a wave and I will find out how much it is moving. But added mass is an interim concept somewhat, right? You do not see it. How do I measure it? That is what my question is. Okay. But having said that, added mass, I said yesterday, is basically a force concept. There is nothing like identified mass, it is added mass force. So, you can immediately understand that the measurement system must consist of measuring some kind of force. So, that is point 1. Point 2 is that, see, I know that this T equal to natural period equal to like 2 pi into mass plus added mass by C. Now, here I know this for a geometry, I know this for geometry, I have to only know this added mass. So, if I were to take a body and just push it down, it might go like that. So, I can figure out this period and I can say, well, I know this, everything I know, I can find out this. Okay. But there is something wrong. What is wrong? What I found out this is only for this period. Remember, this A is a function of frequency. See, I have no choice on the frequency period. Let us say it is 11 second, scale down version maybe 3 second. So, what I found A is only for 3 seconds. So, in order for me to find out added mass, which is over all frequency, I have to conceive a different experiment. Okay. Very important to understand that. So, this is what is called, what we are going to talk to a little bit, is called forced oscillation test. In only one mode heave I will tell, forced oscillation test. In fact, you can we can do that in our tank with the dynamometer we have, provided we have a forced mechanism. What we do here, this is my tank here, see, water tank. So, let us put the water like this, and I have the body here. What I do is that, see, I want to give it a particular oscillation motion Z or say ZA E I omega t. I am controlling it, omega and ZA. I can have a mechanism, some kind of circular mechanism by which I push it down. Then what I do, by an instrument here, I measure the force that is been required to push it down, the force that is coming. Okay. So, what I do is that, remember this force oscillation test, for a given known frequency omega and for an oscillation amplitude A, which should be sinusoidal, I am measuring Fz. Okay. Once again, let me tell you this, I have this body, I oscillate it. Oscillation frequency is decided by me, like I want to do the test for this frequency, run number 1, omega equal to 0.1 to 0.15, like that. I decide a amplitude 1 centimeter or whatever. These are my input, but this is the interesting point. See, I am doing that, of course, fluid sets up a pressure field here. So, therefore, I have to work against the water. So, there is a force coming, and that is what I measure by an equipment here. So, I measure the force. Now, from this I can find out, you see, this is called forced oscillation test. I can find out the added mass and dumping. How we will tell? You see here, the interesting point is that I will just work it out. My Z here equal to ZA, I will write it again, e power of, well, we can do it plus or minus, does not matter, a real part is implied. Now, if Z that I measure, it becomes F an amplitude, let me call it O, e power of I omega t plus beta f. You see why this? Because remember that, how I get this beta f, I have oscillated that, oscillation is this is what I have given, right, input data. This is my ZA, if this is my period t, This is my 2 pi by omega, agreed. See, I have oscillated that, so I know of course ZA period 2 pi by omega, etc. What did I measure? The force history. Remember history. So force looks something like this. This is the output. This is what I have measured. The equipment have measured me this force. See, the equipment have measured me this force, that every second I plot that. Okay, when I plot that, it is likely to be it will be sinusoidal. Actually, for that purpose, I would do some kind of a filtering, feeding, etc. But it will be taken as a sine curve. What do I get of that? The amplitude here, that is my this, and I will know the phase. Remember, that is important. This phase. This picture may not be correct, but the point is that I would know both this and this from the measurement. So, I have fed this and I have fed this. What I found out is this and this. Okay. This is always a harmonic test. So, I once again repeat, this is input, this is in for a given omega. Output is what I measured is f0 and beta f. Now, from there how do I find added mass? This is what I have put in and what I measured. Now, how do I find added mass? We will go to that. So, now we have to go back to this equation of motion for heave, m plus, we will work it out slowly. Oh, sorry, not m plus a, or rather let me cut it again, a z see, in this case I have got f0, let me write in a complex number only, I omega t e I, let me just call it beta. Remember that this and this we have found out, remember this f0 and this. Of course, z equal to ZA e I omega t. So, what is z dot equal to? Here I have written plus, actually this plus minus, remember again, the way you proceed really does not matter. You can always write this as minus, plus, something else instead of sine, cos, the answer will be the same thing. I am only showing therefore the principle of how we go proceed. So, here I wrote plus, I could have written minus also, did not matter, because both of them are cos omega t, remember real part. So, this has become I omega okay. How much is z dot dot? Minus omega square. So, what happens to this equation? Minus omega square m plus a z z a, right, e I omega t, that is right, because z a comes here, e I omega t comes here, minus omega square z double dot, this is okay, no? Next term is plus I omega z a b z, that is okay, b z into I omega z a, this thing. The next one is c z into z a e I omega t, this is equal to f 0 e I omega t e I beta. Okay. Now, we can delete all this. So, I end up getting minus omega square m plus I omega, let me just see this also. Okay, I omega z a b z plus c z this is okay. see this you all agree with that, no? See, minus omega square m plus az za plus I omega bz z za bz cz za equal to f0 e I beta, that is f0 cos beta plus I f0 sin beta. So, now obviously from this equation real part is real part, imaginary part is imaginary part. So, you end up getting the two equation from which you can find this thing. So, what I end up getting is minus omega square m plus az za plus cz equal to f0 cos beta, and well I omega za bz equal to I f0. Of course, from there this is 2, say this is 1, from 2 I get straightforward bz equal to f0 sin beta by omega za, and from 1 I can get az. Well, I can get az as, let us see how, f0 cos beta minus cz za divided by omega minus omega square za minus m, something like that. See, this divided by minus that gives you this, you divide by omega square za, then take m on that side. I mean, you can work it out whichever way. So, what I mean is therefore that this is what is called force oscillation test, which is what you could do to find out basically your like added mass experimentally. This is a very important test. Why I mentioned to you this now in the class is because usually this is not so commonly known to people, because many tests you do for design purpose is to directly find the output, but here you are finding added mass. See, added mass is just a quantity which would be useful tomorrow if you want to predict ship motions, but you are not measuring ship motion directly, remember. Okay, like resistance you are measuring directly, somebody can figure out, oh, so many kilonewton is the total resistance. Metacentric height you may be measuring some time, you may be yeah, kg you are measuring in your inclining test, but here added mass, if you go to industry and say I want to measure added mass, people will not know about it. So, therefore, this experiment for added mass measurement force oscillation is not usually commonly known, that is why I am trying to tell you. And you can also see here that experimental measurements here are not so direct, you have to make certain assumption, you measure something and go through certain equation to get something ultimately. That is very important, and this also involves inherently a phase concept. You have to measure phase. Without, suppose beta was, in fact, you will see if beta is 0, bz is 0. That is what will happen at high frequency. You will find out that beta becomes very 0. In fact, one can again find out the same concept as I mentioned, that this is z, z dot, this is my f, this is my beta, this is my f. The kind of like how much it is lagging or leading, one can relate to that in principle. Okay. So, this is what is about this added mass. Now, of course, you are doing a scale test, you are not doing a full scale, you cannot have a full scale ship doing a test. So, what is the scale factor? Another point that I should understand, scaling factors when I do a measurement. Okay. Added mass will scale at what? See, added mass is proportional to mass. So, obviously, it will scale lambda cube, right? Yeah. Tell me how, with what damping will scale. This is important, I want to tell you this. See, maybe before that we should go to time part. Omega square is gk, okay, and t square is how much? T square will be 2 pi square by omega square. T square is going to be 2 pi square by omega 2 pi square by g into k, right. 2 pi square by gk, whatever. I mean, it's opposite. See what I am trying to say, it is t square is this thing with 2 by lambda, and omega square is in proportion to 1 by lambda. Now lambda is wavelength is scaling, well, wavelength here, wavelength is lambda here, let me call it LW, sorry, otherwise you will have a confusion. See what I am saying once again, please understand, omega square is gk, okay. That means omega square is inversely proportional to wavelength LW. You agree with that? Omega square is inversely proportional to wavelength. Say t square is linearly proportional to wavelength. Now wavelength obviously scales at lambda. So frequency will scale at what? 1 by root lambda, and t will scale at root lambda. This is important. That means if natural period is 10 for actual body, 1:10 scale body would have a period of 1 second, 1 by root 10. Please understand this very importantly. If a natural period of a ship is 10 seconds, its 1:100 scale model would or should have a natural period of 1 second. If the frequency there is, well, 10 second means 2 pi by 10 means about 0.6. Here it is going to be 2 pi by 1, 6. So frequency is much faster, but period is much smaller. They are not linear, square root. Why I am saying this? Because in Bz I need that. Now let us work out how do I scale Bz. Anybody knows? You see, how do I scale? Remember Bz into z dot. This is a force. Okay, this scales at lambda cube because force scales at lambda cube. Now z, what is z dot? Dz by dt. How does it scale at? Lambda by t is root lambda, that is scaling at root lambda. So what should Bz scale at? Absolutely. So Bz scaling at lambda power of 2.5. Everybody agrees? Bz should scale lambda power 2.5. Very simple to work out. What about Cz? Immediately one can tell, because Cz is, first of all, exactly, because it is C into Z. So this obviously this is lambda, so this must be lambda square. So I will just organize and write it down. Therefore, the scaling factor has become C. Az is lambda cube. Bz or damping, once again will come to a next level. This is all linear motion, 2.5. Cz equal to lambda square. Omega of course scaled with root lambda, 1 by root lambda, and t scaled with root lambda. So this is linear. You please work out yourself what will happen to dyy and b theta and c theta. Because there are moment there. What would happen to moment? Force into distance, another L gets multiplied. So you will end up getting this part. It's not going to be just 4, because moment of inertia, mass into distance square. So I will leave it to you as an exercise to work it out. You can work out from elementary example, but let's look at c theta straightforward, because it is rho g into v into gml. So this is lambda cube, this is lambda, so lambda 4. So you will see it's lambda 5, lambda 4.5. Why this not 4? Because remember it is theta dot dot, not z dot dot. There is one lambda gets out from that side for moment, because the motion here is theta, which is actually only there is no L there. In other words, I tell you I into theta dot dot. This is my lambda 4, but this lambda 5 and this is 1 by lambda gives me lambda 4. So you can work it out, this scaling. Very important to understand the scaling, because I do a test, I don't know how to scale up, I have no really meaningless thing. All right. All right. So this brings me to some simple kind of a like problem type. I thought I will spend some time to tell you about some very simple problems. Let's see this. I have a ship. I am standing here. Now I find out that at a speed of v equal to say 18 knots, when waves are coming opposite, okay, I find some regular wave field. I am heading into that, and I find I have excessive heave motion. Okay. I have the ship parameters given. Please understand, I have the ship parameters. This is known. All the ship parameters is known. Okay. I have a ship. Of course, I know the hydrostatic parameters are known. I find out that in some wave condition, waves are coming heading on at a certain speed, 18 or so, or some given speed, I have excessive heave motion. The question is, can I guess the length of the waves? Waves, the wave field, wave is regular wave field. That means, what will be the lambda? Problem is very simple, because excessive motion means obviously wave frequency, exciting frequency omega is equal to natural frequency omega z. That means, and this is equal to, of course, we know root over of c by m plus a. Of course, I have to make some estimate of a. Without that, you cannot proceed. So, how do I go? I can estimate a. I of course know c and m from hydrostatics and mass inertia. So, what will happen from there? From this relation, I will be able to find out my, well, I know the natural period. So, I know what is my omega e. Once I know omega e, I can go back to the relation omega equal to omega into 1 minus omega v by g cos mu. Mu is given here. So, I can find out omega. Once I know omega, I can find out lambda. So, if you do that, I thought, say this problem, I will give it to you with the numbers here. See, this shape is there, let us say displacement of 20,000 ton. Okay. Assume added mass to be equal to mass, which means added mass coefficient Az bar, or what, I do not remember what I took, but Az bar as 1. You take it as that, you assume that. Water plane area I need AWP. Well, actually sometime, you know, what will happen is that we will give L and B and then CWP, etc. Say AWP is also given. It can be maybe 1500, which is 100 into 1800 meter square or something like that. Okay. Find out the lambda for 18 knots. So, let me organize this and write it properly, otherwise probably you are getting this thing. So, I have displacement of 20,000 ton. Actually, let me put the other way around, L of say 150 meter, B of maybe 20 meter, which is of course no, let me 30 meter, right. I do not want to make it this thing, this 28 meter I make it, okay, because 30 makes it L by P 5 is too short, 25 makes it L by P of 6, so 25 is good number. T of 10 meter, let me put it, deep vehicle, CB of 0.75, CWP of 0.78. Say these are all given to you, okay. Assume Az bar to be equal to 1. Wave heading (180°) head waves. Excessive at 18 knots. in regular wave field. What is the please remember that this is a forward speed problem. So, the omega you find out is omega e. Omega e is equal to the natural period, natural frequency. Omega e is not omega is equal to, remember that I mentioned here also. It is this, because some people make this mistake, you know, instead of omega e you say omega equal to natural period, and then in other words you find out the natural period. Let us say natural period happens to be, let us say something like 10 seconds. So, you think 10 seconds is omega and find out the wavelength. Okay. Some people do that, it is wrong because this is omega e. So, from omega e I have to first find out omega and then find out what is the wavelength for that omega. Okay. So, I am repeating this because this is a common mistake people make. That is one common mistake people make, and the other common mistake people always make is in delta IYY and IYY part in pitch, because people always take IYY for a real. If I give a ship, you know, dimension and all that estimate, I will come to that. They always take IYY to be the moment of inertia for the water plane. Okay. That is another mistake that is commonly made by people. Okay. So, this is a very simple problem we can do, and we can manipulate with that in various ways, because it need not be a like head waves, it can be some 45-degree wave, can be falling wave, but essentially if there is an excessive motion, the word excessive motion means it is resonating. Okay. Now, let us look at another one that I have here. See, there is an estimate of added mass. We just do this based on some kind of a simple calculation. We have another maybe 5 minutes. So, here it says I have a wooden log of uniform cross section, or let us take a barge. I have a barge here of uniform cross section, which can be any uniform, of side B, width B, length L, okay, and it is statically stable. Now, here once again the question I asked was what is my Tz and T theta, estimate that. But you see, then I said that use your engineering judgment. I mean, I am trying to leave it to you, use your engineering judgment for that, for estimates. So, you understand now that Tz I require to estimate what? Added mass. The other things are all known. This is a LBT, etc., mass and all is known. See, this is a square bar, let us see, because I would have given also is LB and T and probably CB. So, mass and all is known in this problem. Now, for Tz I need an estimate of Az. Okay. Please do that. How would you do it? Well, I said when nothing is there, simply take this sectional added mass to be B square, and this case is very simple because it is uniform cross section and B is constant throughout. So, I have B square by pi B square by 8 into L becomes Az. You understand the sectional added mass is pi B square by 8, integrated along length is L. That is one part. What is my added moment of inertia and moment of inertia? For T theta I need two things, I need Iyy as well as I need delta Iyy. Remember, let us talk of delta Iyy first. How much it is? It is a uniform cross section. So, I have actually pi B square by 8 into x square integration from minus L by 2 to plus L by 2 dx. This you agree? Because take any section, distance x, sectional added mass is B square by 8 pi, moment of energy into x square, integrate that, actually it will be x cube by 3, and if you work it out you will find out x cube by 3 L by 1 by root 12 or something, very easy. What about this? If you again you have to make an estimate, realistic estimate, make kyy to be maybe 0.25. I would not stick to only 0.25. Suppose you are making 0.30, okay, make it 0.24, okay. No hard and fast rule, but try to make a realistic estimate. If you do that, you will end up getting basically a estimate of these numbers, and that can be off by 10-20%, not a big deal, but at least you get a good estimate. Okay, I still have a few minutes for this, and I want to touch upon just not a problem, one more thing, this relation between this Tz and T theta from design point of view. You see, what would be your objective in a design? Would you like them to be same or different? Obviously, full aim for us would be to make sure that they are separated out, because if they are not separated out, I am going to have, when it is excessively heaving, also excessively pitching. So always, and it turns out, see, this also is around 8 to 12 seconds, this also 8 to 12 seconds. So one of the things the designer needs to worry, and we have seen in practical experience, is that if your design is bad, you actually end up having these two very close by, and these two very close by means a very bad design. Okay. So if supposing it happens, you will have to try to see how I can separate out. Even if you separate by 1 or 2 seconds is good enough, but you must separate out. That is an important thing. It has happened to practical ships that exist where heave and pitch periods are close by, and therefore everybody says they do not want to be on that boat because it is so bad motion. And one of the things that we could do, we will see again, that we will see in a roll motion later on, that an interesting inverse case occurs. You actually might have to raise center of gravity to lower metacentric height, because you see if GM, say in offshore structure, we have seen that periods are in proportional to 1 by root GM. Well, L or T in the case of offshore structure same, we will talk about that in roll. So what happens if it is too high, you have a very high means is low, but I want to have this low, therefore I have to go, basically I must reduce it. This we will see later on, but this for a ship, please remember this, that unfortunately my heave and pitch periods happen to be very close to everyday waves. It is sometimes known as everyday waves, you know, this all these 6 to 12 second, 15 second waves, and as a result at times resonance is unavoidable, and therefore I should try to design where I do not resonate together, so that I have really bad time. So therefore I should design so that heave and pitch are slightly pushed out by a few seconds. That is important. Okay. So with that we will talk, and next class we will now shift to roll motion. Thank you.